Hello, I am Sauradip Ganguly. I am a PhD student at Central Mechanical Engineering Research Institute, CSIR CMERI, India. Currently, I am working on development of non-novel metal-based electrocatalyst for hybrid water electrolysis under the supervision of Dr. Chanchal Loa and Dr. Sirsendu Ghosh. Hydrogen as a fuel has become a priority research topic in the past decade. Hydrogen is considered as a clean source of energy as combustion of hydrogen results in zero carbon footprint. Water electrolysis using renewable sources is one of the easiest way to produce hydrogen. Conventional hydrogen production through water splitting is accompanied with oxygen evolution reaction, which is kinetically sluggish and needs more potential. Moreover, costly separation membrane is required to get pure hydrogen from the cell. So, hybrid electrolysis comes out to be a sustainable way towards production of hydrogen at a lower potential budget, along with the production of value-added commodity chemicals, which are produced from different chemical methods under harsh conditions. Under milder conditions, these commodity chemicals could be oxidized from biomass-derived chemicals. Thermodynamically, the bond dissociation energy of the CH and the OH bonds present in these organic molecules are much lower than that of the OH bond dissociation energy of water. In alkaline medium, iron, cobalt, nickel, and copper-based electrocatalysts were studied. During the anodic sweep, hypervalent metal oxyhydroxides are formed in these 3D metals, which are the active species for the substrate oxidation reactions. Amongst them, nickel-based electrocatalysts are the promising one, particularly in basic medium, owing to the ease formation of the active species, potential advantage, as well as the mass activity. Earlier, we established Ni12P5 is the best active phase among the other nickel phosphide phases for alcohol oxidation. So more optimization is required to maximize the catalytic activity of Ni12P5. In this work, we have shown apart from doping or manipulating the nickel 2 to nickel 3 redox chemistry, the electrocatalytic activity can strongly be influenced by increasing the density of the active sites through facet engineering. To do so, nickel 12P5 nanoparticle were synthesized in two geometry, hexagon and sphere. Nickel 12P5 nanohexagon were synthesized in a kinetically controlled way using oleic acid as capping agent, which stabilizes a particular high index 4 bar 5 bar facet. HTM analysis of nickel 12P5 nanohexagon shows more exposure of 4 bar 5 bar group at top and bottom, along with 1 7 bar 2 bar, 4 bar 4 bar, and 5 bar 2 group of facet as 6 surfaces. While for nickel 12P5 nanospheres, the most exposed facet was 132. DFT calculation also confirms the high surface energy of 4 bar 5 bar facet for nickel 12P5 nanohexagon compared to 132 facet for nickel 12P5 nanosphere. The electrocatalytic alcohol oxidation was first tested with methanol. An abrupt increase in the current density along with the lowering in onset potential is a clear indication of methanol oxidation. Various other substrates like aliphatic alcohols, unsaturated aliphatic alcohols, aromatic amines, aromatic alpha hydroxy acids, and HMA, which is having alcohol and aldehyde functionality, along with urea, which acts as a sacrificial agent, has been used as substrate scope. The peak current density and mass activity of all the substrates for nanohexagon was much better compared to nanospheres. Activation energy is an important kinetic parameter for a chemical reaction to know how fast a reaction to occur in the presence of a catalyst. Experimental temperature-dependent chronoamperometry was studied to calculate the activation energy. Kinetic energy for all the substrates are lower compared to OER, implying kinetic feasibility of substrate oxidation compared to OER. The nanohexagon shows less energy demanding kinetics for all the substrates compared to nanospheres. High Faraday yield and percentage product conversion was observed with nanohexagon for bulk electrolysis. The DFT calculation of binding energy for methanol and benzyl alcohol were studied at both 4 bar 5 bar facet of nanohexagon and 132 facet of nanosphere. The high binding energy was observed for 4 bar 5 bar facet of nanohexagon, indicating improved adsorption of reactants with acceleration of the reaction. For real applications, 2-electrode single cell electrolyzer was designed with platinum carbon as cathode, nickel 12P5 nanohexagon as anode, and 0.1 molar of substrate in 1 molar NaOH as electrolyte. LSB were studied to compare the potential advantage compared to OER. Maximum potential advantage was gained for aliphatic compared to the aromatic substrates due to the low solubility of aromatic substrate in the aqueous medium. In conclusion, nickel 12P5 nanohexagon was synthesized in a kinetically controlled way for exposure of a particular high index 4 bar 5 bar facet. Electrocatalytic activity and mass activity for substrate oxidation was way ahead for nickel 12P5 nanohexagon compared to nickel 12P5 nanospheres. For bulk electrolysis, high percentage product conversion along with a high percentage Faraday yield was obtained with nickel 12P5 nanohexagon. The study displays kill two birds with one stone approach to couple hydrogen industry to chemical industry. I want to sincerely acknowledge my supervisors, Dr. Sirsendu Ghosh and Dr. Chanchal Loa, for support and guidance. Also, I want to acknowledge DST Inspire Faculty Fellow Scheme for financial support to do my research work, and CMERI for providing lab to do my research work. Thank you. Hope you like the work. For more details, you can go through our article.